It's okay. Okay, I'm going to erase. Okay, and now let's put everything together. Let's put everything together. Again, I repeat again. Okay. Okay, so balance forces means no net force or no resultant force. Okay, it's the same thing. 一样的东西来的 net force 跟 resultant force. Sometimes you see resultant, sometimes you see net force. Okay, now balance forces, there are two possible situations. Okay, again, I repeat, two possible. First one is the object at rest. Okay, so for object at rest, the gravitational weight is balanced by the reaction, normal reaction. Okay, now, or it can be the different situation. The object is moving at a constant velocity, let's say 5 ms minus 1. Okay, moving at constant velocity. So in this case, the forces balance here is first is W balanced by the reaction, and maybe this is a force 5N here balanced by a friction of 5N here. Okay, a ball is moving and then there's a friction, same with the force applied. So in this case, also there's no net force. Okay, if you minus all, you get 0. So in this case, it can be moving at constant velocity. All right. So these two cases, remember these two. Okay. Now, if you take a look at these two scenarios, right, it tells you about something, the Newton first law of motion. I think you have learned about the Newton first law of motion. Okay, if you haven't learned about that, you can just easily go and look at your textbook. Then you'll see what is the Newton first law. It's basically, it says that if there is no net force, I write down here, if there is no net force acting on a body, its state of motion will be unchanged. Okay, so this is the Newton's first law of motion. It says that if there is no net force acting on a body, its state of motion will be, grammatical error here, unchanged. Okay, you know that. Okay, unchanged. Now will be unchanged. So this one is the Newton first law of motion. So basically, it says that for just like these two is situation. Okay, so the first situation, the ball is at rest. If there is no net force or there is no external force, then it will continue at rest. It won't suddenly move one. If it suddenly moves, then something is wrong. Okay, now the second scenario, if a ball is initially moving, okay, without external force, if you don't apply any external force, then it will continue to do so, continue until forever. Okay, now it will continue to remain its state of motion. State of motion is like whether you're moving or you're at rest, or this is your state of motion. Okay, so you see this Newton first law of inertia. Okay, yeah, before I forget, this one is called the inertia. Inertia. This is what Newton is talking about. Inertia. So you see this inertia everywhere, just like when you are in a bus. Okay, you're moving in a bus. Okay, with the bus together. So let's say the bus is moving at 10 km per hour. Then your body is also moving at 10 km per hour. But suddenly, now at this point, you are what state of motion you are in? You are in motion. You are moving. Suddenly the bus stops. You step on the brake, Okay, you see the red light in front, and you step on the brake, suddenly it stops, and then you are thrown forward, right? You are thrown forward. Okay, what happened is because of your inertia. So initially you are in a state of motion, which is you are moving, but suddenly the bus stops, but your body tends to continue the motion because of your body's inertia. It is because your body tends to continue the motion, so which is why you are thrown forward. All right. Same with what else? What examples like ketchup? Okay, 你要倒那个 tomato sauce 出来 ，OK， you how you what do you say？ You like 你这样子倒的那 tomato 是会 slide 出来嘛，是不是？Because you provide a forward movement, then suddenly you stop, right? Suddenly you stop, then inside it comes out because it tends to retain its motion. You can see a lot of examples of this one. Okay, so in your book, okay, I'm just giving you a few examples to maybe to help you in understanding it. All right. So this is inertia. So again, inertia is the ability of object, or you can say the tendency of object to remain its own motion. Okay, all object remains its own motion. Now, different scenarios of balance forces. What are other examples of balance forces? It can be a pendulum. Let me draw it. Let's say this is the block and a hanging pendulum. Okay, now label the forces here. Label the forces. So you have what else? What is the first step to label? W. Okay, so in this case, now since in this case the pendulum is not on any surface, right? It's not in contact with any surface, but it is in contact with a string here. This is a string. So in here, there's no normal reaction, but the force here is what we call as tension, T. Okay, so label tension in springs. In springs, we use tension. All right. So for surface, we use reaction, R. So this one is T. So we can say that T equals to W. Are you sure you can hear me? It's very laggy, I feel like. Okay, never mind, I talk slower. Okay, so the first scenario, this one, balance force. Second one can be, let's say, let's take a simple one. A bird perching. Perching on a tree. So what is the force? Weight. So there's a surface here, the tree branch. So there's normal reaction acting up. Okay, or it can be a plane traveling at constant velocity. Okay, a plane traveling at constant velocity. So this is let me draw like simple something like that. Okay, plane traveling at constant velocity. So it is balanced by what? It is balanced by the weight of the plane with the, what is this? This is the lift generated by the wings, and then there's friction, right? So there's a thrust due to the engine. This is the forward force. So L is equals to W, and the thrust is equals to the drag. T equals to D. This one is for airplanes. Okay, so all the forces are balanced. So as a result, the plane is moving at this constant velocity, right? So if the plane wants to accelerate, if it wants to increase its velocity, it needs to apply a net force, right? It needs to apply a net force, and that's when he increased the thrust. Okay, so he increased the thrust, making the T bigger, now bigger than D. So the net force is acting to the left, and that's how it increases velocity. In other words, it is accelerating. Okay, so now let's look at unbalanced forces. Okay, hope you don't fall asleep now. Another 23 minutes, then we can proceed to exercise. Then let you do the exercise. Okay, unbalanced forces. Okay, let's consider a block of mass. Let's consider a block of mass 5 kg on the surface. And there's horizontal force of 10N acting to the right and horizontal force of 5N acting to the left here. Now label all the forces. First step, label all the forces. First, what you label? W. Okay, so it's on a surface. So R, W and R. Is there any other force? No. The other two forces is just 10N and 5N. Okay, now calculate the net force. What is the net force here? 5N acting to the right, 5N acting to the left. We just take 10N minus 5N. So net force acting to the right. What is the magnitude of the net force? You just take 10N minus 5N. So 5N. F net is 5N. Okay, now calculate the weight of the object. So W equals to mg. I'm sure you all learned about this one already. W equals to mg. M stands for mass. G is the gravitational acceleration, which is usually 10 meter per second square, or sometimes we use 9.8 meter per second square. It depends on your question. Okay, so in this case, we use 10 for simplicity. Right, we just use 10 meter per second square. So 5 kg bracket 10, so it's 50 Newton. This is the weight. Weight is 50 Newton. Now, I'm sure you know the difference between mass and weight. Okay, so mass is just the amount of particles in an object. It stays true everywhere. Whether you're on the earth, whether you are on the moon, your mass will not change. You weigh 10 kg, you weigh 60 kg here, you also weigh 60 kg on the moon. But weight is a measure of the gravitational force. It has nothing to do with your real mass, which is why your weight changes, depends on where you are. Okay, it depends on the gravitational force of the planet acting on your body. Okay, it depends on the distance, right? So two different things, mass and weight, right? So I don't need to talk about that one. I think you know already. Sometimes I just want to remind you, right? Now, so for this case, what will the object end up doing? The object, the block of mass will end up moving to the right because there's force acting to the right. Now, not only it is moving to the right, it is accelerating to the right. Okay, pay attention to my word. Because there's a net force means it is accelerating. Now, using Newton's second law of motion, what is Newton's second law of motion? If you look at the textbook, it says that Newton's second law of motion, it says that F equals to ma. Okay, F equals to ma. What does it mean? First, force. This one, note this one. This one is the net force. This one is the net force or resultant force. Okay, so many people get the mistakes is because they don't know this one F. Sometimes they forgot this is the net force. Okay, later I will show you an example why. Okay, so F is the net force, remember. So M, mass, and A is the acceleration. Okay, so when there's no net force, then there's no acceleration. If this F is 0, no net force, meaning that force are balanced, then your A is 0. If this force It's not 0, then your A is accelerating, the object is accelerating, which is why in this case, if I want to calculate the acceleration of the object, I use this formula. How do I calculate? F net is 5, so meaning that I have to take 10n minus 5n, right? So this one is acting opposite, so 10n minus 5 equals to 5a. So 5 equals to 5a, and a equals to 1 meter per second squared. So every second, the object will increase its speed by 1 meter per second. This is the acceleration due to the net force. All right, not complicated, huh? Okay, not complicated, right? Okay, now another one. Let's say block of mass 5 kg. Now in this case, I want to lift up the mass. I want to lift it up. Okay. Again, what forces is acting? First is the W, weight, and if I want to lift it, I need to apply a lifting force L. I can just label F lah, same thing. Okay. Now, if the force I apply here is equals to the weight, does it move up? If the force, let's say the weight is 50, and the force applied, I also applied 50 force. It's balanced, right? It's balanced. Up and down is balanced. Does the object move up? It could. It could, okay? It can be moving up, but provided it has to move up at a constant velocity. Recall what we have learned just now? Constant velocity also means the force is balanced, okay? Okay, so 50, if you apply the same force as the weight, it can be of two scenarios happen. The first one, the object can move up at a constant velocity. The second one, the object stays at rest. The object stays at rest just like how it is right now. Okay, now if you apply a force that is greater than 50 Newton, for example, 60 Newton is greater. So in this case, you are creating a net force acting upward, net force. So in this case, the object no longer moves at a constant velocity. It accelerates because there is a net force. Okay, so object accelerate upward. Okay, now almost we have left a little part, then I'll just give you the exercise to try out. Okay, what else? Okay, F equals to ma. Let's look at the formula F equals to ma. Let's look at Newton's second law. What is Newton's first law again? First law states that an object will continue its initial state of motion. If the object initially is moving, it will tend to continue moving if there is no external force. Okay, so object at rest, it will tend to continue at rest if there's no external force, unless you go and create the external force, you go and lift it, you go and disturb it. So in this case, you're disturbing the system, right? So notice the word I use here, system. Okay. So in physics, you always use all these terms: system, net force. Okay, all of this. Now, okay, nothing special about Newton's nothing special about Newton's first law. Okay, it's just very boring, right? Now let's go to Newton's second law. Second law is F equals to ma. Now notice that before this chapter, we learned about momentum, right? Momentum. So what is the impulse formula? Impulse is F times T. This is impulse. Momentum, change of momentum. Okay, this triangular shape means change. You learned that one in maths. Change of momentum is mv minus mu. Okay, final momentum minus initial momentum. That is change of momentum. Now what we learn is the impulse is equal to the change of momentum, right? Now from here, if I move the t over there, so F equals to mv minus mu over t. Okay. Now this force is we call the impulsive force. Just like the example just now, when a ball is thrown at your face, you feel the force. That is the impulsive force. Okay, and the larger the larger the the shorter the time taken to hit your face, okay, the higher the impulsive force. Okay, the shorter the time of contact between the ball and your face, the higher the impulsive force. Okay, now from here, from this formula, if I take out the m, factorize the m out, so m equals to v minus u over t. I factorize the m out, so m f equals to m, and then I can write as v minus u divided by t. Right? So let's continue here. So f equals to, what is this? What is v minus u divided by t? So final velocity minus initial velocity over time. This is the acceleration. Okay? Acceleration is final velocity minus initial velocity over time. So that's how you get f equals to ma equation. So this is the Newton's second law. And the Newton's second law states that Newton say that the higher the resultant force, okay, again this is the net, this is resultant net force. Newton's second law says that the higher the resultant force, the higher the acceleration. Yeah, it's just that. Basically, it's just saying that. Okay, so Newton's second law, remember F equals to ma. Higher resultant force, higher acceleration. Okay, we left two minutes here. Let's do the same again, log out and log back in, okay, for the last time. I think this is the last time, okay, because they only allow 40 minutes. Okay, so I'll invite you again.